Let's then move on with today's talk. So it's my pleasure to introduce today's speaker, Anton Akhmerov, and I'll just briefly introduce him before giving the virtual floor to him. So Anton graduated with his PhD from University of Leiden, 2011, and then after staying there for a brief postdoctoral stay, he went to Harvard for, was it only a year, I think?
Yeah.
Something like that, yes. And then already in 2013, he returned to Netherlands as an assistant professor at the Department of Quantum Nanoscience at the Delft University of Technology. And then he's still there, and since 2018 as an associate professor. Anton is a theoretical condensed matter physicist, broadly working in the areas of graphene, topological insulators, and Majorana bound states. I think he's particularly well known for his work on the Majoranas and their use in quantum computing. And also he's one of the developers of this software package Quant for numerical quantum transport simulations. And he's also a strong advocate for open science and collaborative development. Yes, but only the first online colloquium today, so well, this will be open at least. And I think with that, so the topic today is Majorana fermions. The title of Anton's talk is Tinkering with Majoranas. And thanks for accepting our invitation, and I really look forward to your talk.
All right. Thank you very much for the invitation. Let's see. The screen share should be up and running. Everything good? Yes. All right. First of all, it's my first experience delivering an online colloquium, so I hope it goes smoothly, and I hope everything goes well. Thanks to Peter and Jose for the invitation, and I'm really excited to try this format from the presenter side. I have participated as a viewer in quite a few. Also, a quick shout out. I'm together with, I see Julia also here, an organizer of a member of the Virtual Science Forum, which is a big name for a few people trying to accommodate online events. So please, if you want to run, for example, an online session, and I imagine since many of you are in atomic scale and microscopy, many of you have actually seen and participated in the last week's session organized by Julia and Marina. I also see here, and some other people. So I think now is a great time for these events. Anyway, my talk. First of all, I am going to cover reasonably much ground. So, and I also realized that I am somewhat alien here, because nothing I'm going to talk about is quite atomic scale, and to you these systems might appear huge. So please do interrupt me with questions and at any time. Well, okay, raise hand, and then I'm also keeping an eye on the chat and looking at the raised hands. So I'm going to talk about several works done by done in my group. That's us. Just a moment. Yes, Quantum Tinkerer. Indeed, most of it is numerical or numerical to a large extent. And in all these papers, if you're interested to go in more detail and easily try it for yourself, you can get the source code, run it, and observe the results. All right. Now, another announcement before we begin. This is my department, the quantum nanoscience. So I work roughly over here on the third floor. No, wait, yeah. Now, unfortunately, I haven't been there for quite a while, especially in summer. It's very pretty, as you see. But something that might be perhaps relevant to you, we are hiring. So, in particular, we are interested in experimental positions, something which generally fits into the theme of quantum sensing. Now, with all the announcements out of the way, let me proceed. So this is the rough plan of my talk. First of all, I will, just as a start, I will explain the canonical story of Majorana's, and this can go faster or slower depending on how familiar you are with Majorana's. By the way, this is probably a good point to check. How many of you know, let's say, the basics of Majorana's? Can you please click yes if you do know this and no if you don't? And I see a question by, no, not a question, that was erased. Okay, I see a bunch of yeses, but also a handful of no's. So yeah, it's roughly 2 to 3-ish. So all right, thanks all. I will try to explain the story. So I'm going to explain the canonical story. I'm going to highlight a couple of problems that you might have missed if you are an outsider to the field, and these are the complications in the story. And also I will share something a recent work that I'm really excited about, and how we can use device geometry to solve one of these problems. At this point, you probably noticed the parking sign in the corner. That's this. And you might be wondering what this is about. And this is where you can park my floating face so that it does not obscure your screen or my slides. And once it's parked there, you can keep it there. I promise to not use this area of the slide. All right, so the basic story of Majorana's. First of all, a Majorana fermion, or perhaps I should rather call it a Majorana bound state, is a quantum particle that whose creation operator and annihilation operator are equal. Additionally, similar to regular fermions, different Majoranas anticommute. So this sounds very mathematical, but we can make it more understandable by observing two properties. First of all, if I have two of such operators, then only using their anticommutation relation, I can observe that they too combine to a regular fermion. So to put it differently, since we don't actually have Majoranas in the physical world, I can take a single fermion and I could split it into two Majoranas. Now, another important property is that if you take one Majorana in isolation, you observe that the Hamiltonian does not allow to include any local terms. So there's nothing that you can couple a Majorana with, or in other words, an isolated Majorana has absolutely no energy cost, which means this fermionic degree of freedom encoded in two Majoranas has absolutely zero energy if the two Majoranas are separated. And therefore, it hides a quantum degree of freedom, whether the fermion is present, is occupied or empty, from the environment. This is a building block of a topological quantum computer that relies on this protection by non-locality in order to get rid of decoherence. But I realize this is all very abstract. So let's see how making Majoranas looks like. First of all, Majoranas require several several underlying common principles. First of all, in order for a fermion to be hidden from the environment, you need the fermion number to not be well defined. Otherwise, you can just count them. Thankfully, superconductors provide that. Superconductors allow creation and annihilation of Cooper pairs, so they only preserve fermion parity and not the fermion number, and therefore superconductors can host Majoranas as well. Now, Majoranas also need to be isolated. That means we need to break a time reversal symmetry, because otherwise Kramer's degeneracy would result in all the states coming doubled. And we need to break spin rotation symmetry for exactly the same reason. These are the basic ingredients. They can be taken from many different sources. And indeed, there are probably dozens by now, maybe approaching 100 different proposals of how to make Majoranas. Different systems, topological insulators, unconventional superconductors, conventional superconductors, 1D, 2D, 3D, a lot of those. But I'm going to focus on one topic, that is one specific idea, which is perhaps the most active, and it is a one-dimensional proximity structures. Here is how these look like. So what you're viewing here is a semiconducting nanowire that is coupled to a superconductor. Now, the time reversal symmetry is broken by an externally applied Zeeman field. And finally, the intrinsic spin-orbit coupling of a semiconductor additionally breaks the residual spin rotation symmetry. So once we apply a magnetic field that is strong enough, we obtain Majoranas in this device. The Majoranas would appear at the edges of the nanowire. Oh yes, and of course, these electrostatic gates are controlling the local electron density to tune the semiconductor or the nanowire in the correct regime. Now let's look at this system in more detail. So first of all, we start with a band structure of a superconductor. That's a typical Mexican head potential, Mexican head dispersion relation. At around k equals to k Fermi, there is a superconducting gap, and you can recognize the residual of a regular parabolic dispersion from the normal state. Once we apply magnetic field, this dispersion becomes more complicated. There's spin splitting and all, and there is and once we make the magnetic field strong enough, we can close the topological gap and reopen it at zero momentum. This is what creates Majoranas. So now the standard way to analyze or to represent such topological devices is a so-called topological phase diagram, where we plot parameters of interest across the axis, and as color we denote, so the topological regions we denote in color, and then depending on how well we understand the system, we could also plot the magnitude of the gap. If you remember, Majoranas require, so Majorana protection relies on spatial separation. And therefore, the larger the gap in the topological regime, the better the Majorana properties. Finally, so here you can see a topological phase diagram in a minimal model where every conduction band contributes a single hyperbolic shape to the topological phase diagram, and in these regions, the system supports Majoranas. All right. Now, if I turn to probing the system, then I think the most common go-to idea is to use the tunneling conductors. So if I look at the system, I would send current from one side, and I see what. So sometimes an incoming electron will reflect back as a hole, and the Cooper pair will enter a superconductor, and I will see Andreev transport that will tell me something about this device. So Majorana states are special in that due to particle hole symmetry or due to their protected properties, they're guaranteed to have a quantized zero bias peak in conductance, which has a height of 2e square over h. There's a beautiful mathematical proof of this that does not rely on, that does not require knowledge of any geometrical details and only relies on the fundamental symmetries of the problem. That is the basic story. Let's now see how it becomes more complicated if we turn to more detailed models of devices. This is there was a work in 2012 that observed that if the electrostatic potential changes smoothly near one of the ends of the nanowire, so it vanishes, and if the spin-orbit coupling is sufficiently weak, then in a trivial regime with a rather low magnetic field, one can still easily get end states that have an exponentially small energy, very similar to Majorana's, but that come in pairs. So these states are, there are different names in literature. I prefer to call them quasi-Majoranas because these are like two Majoranas sitting right on top of each other. There is so I think an intuitive way to understand these states is to think of them as Majoranas, but separated in momentum space and not in the real space. Still, of course, these do not have all the nice properties like protection from all the local perturbations, and any defect will couple them and split them. Of course, these, since there are two, one wouldn't expect these to also contribute a quantized conductance speed. Or so we thought. But then this was actually I think I first heard this realization from my colleague Michael Wimmer, but there were also a lot of people thinking in parallel about this. The quasi-Majorana states that appear near one edge have a nearly orthogonal spin structure. And that means that the effective tunnel barrier strength that the two quasi-Majorana states encounter is also exponentially different if the tunnel barrier is smooth. So if I'm probing conventional Majoranas, I'm going to see this one that is strongly coupled across the barrier, and the one that is far away is going to be very weakly coupled. If I'm probing quasi-Majorana states, there's one quasi-Majorana state that is strongly coupled and one that is weakly coupled. So in other words, the situation is extremely similar. And tunneling conductance might not be a very good probe. So let's see how the conductance with quasi-Majoranas looks like. So this is, so here you're looking at the honest, actual Majoranas. Here you're looking at quasi-Majoranas. So in one case, the system is in a topological regime, and the potential is, and the confining potential is sharp. In the other case, it is smooth. And you see that both Majoranas and quasi-Majoranas provide a really nice zero bias conductance peak that is quantized, nearly similar shape. There is one important difference. If I try to lower the barrier even further, quasi-Majoranas go to 4 e square over h, because there are 2 states after all, and if I remove the barrier completely, both of these states contribute a quantized conductance. But Majoranas instead, since there's only one, they stick to 2 e square over h, forming a zero bias dip. I don't think this was anything like this was observed. And moreover, there was a recent work indicating that we should be worried about quantized conductance as a probe of Majoranas. This was a work led by the group of Sergei Frolov with several collaborators, and they observed that if they make nanowire devices that should definitely not have Majoranas, they can still see quantized conductance plateaus. So that's one problem. Even if we see a quantized conductance peak, we are unsure if these are Majoranas or not. There's another problem, which actually I think is probably even harder to tackle, and it comes with a tip. So if you find yourself in a situation when you need to review an experiment about Majoranas, there's an easy way to do your job well. And in fact, most of the referees did not. So what you should do is you should look at the experimental probes that the authors present. They are probably going to claim that there are Majoranas in their device, but check if there is an evidence of the superconducting gap. Because remember, Majoranas should only appear if there is if they are separated by a gap. It turns out once we turn on a strong magnetic field, superconductors really don't like that. And most of the existing experiments, once you turn on a strong magnetic field, you see essentially no gap. This doesn't only apply to nanowires. This also applies to say atomic chains. So the problem of a lack of topological gap is quite universal. So let's see how we could try and probe if there is in fact a gap or not. One idea here is to change from probing local conductance that does not quite tell us about what is happening underneath the superconductor to non-local conductance. So imagine we are injecting an electron here, and we are seeing what is exiting the device at the other end. So in this case, if the superconductor is indeed gapped, we should see a very weak non-local signal, because all the quasi-particles will be reflected. However, if we have closed the gap, we should so this quasi-particle can convert into from an electron to a hole. So the charge of it is not quite quantized. You could see either type of current, but at least you should see some current. In other words, if I am trying to drive the system through a topological phase transition, I should see first of all no transport at low excitation energies or low bias voltage, no non-local transport. And then once I have driven the system to a topological regime, I should once again see, when I approach a phase transition, I should see the gap closing, and I should see transport at all energies. And then finally, as I reopen the gap, I should see once again no non-local transport. Let's see how it looks in a simulation. So this is non-local transport across a Majorana phase transition. At zero magnetic field, you see no non-local transport. then you see finite non-local conductance at essentially all bias voltages. And then as you go further into the topological regime, you see a well-developed topological gap. There's an interesting corollary to this observation that is more specific to Majoranas. Namely, not only should the gap close and reopen, but it turns out that due to the Majorana charge neutral nature, every Majorana is exactly half a fermion. The shape of this non-local conductance has to be odd. So if it's positive at the positive bias, it should be negative at the negative bias. In other words, if I inject particles with a slightly positive energy, they would come out predominantly as electrons. If I inject particles at a negative energy, they would come out predominantly as holes. That's the story. Since I think it has gotten some traction in our community because it is a new bit of information that you could use to characterize the systems better. So I was really excited to see, I think it was a couple of weeks ago, a paper from the Copenhagen group, but I think Andrew Higginbottom and Lucas Kasparis are the ones that are leading the effort, and Dennis Puglia is, I think she's in IST Austria, and so is Andrew. Anyway, so they did essentially a very similar experiment where they probed non-local conductance. Like in many jokes, there are good news and there are bad news. First of all, they do see that the non-local conductance is odd. That's great. That is what we would expect from a topological transition. The bad news is that they do not see anything that could be characterized as reopening of a gap. They just see once the gap closed, it stays closed no matter what. That's too bad. So these two problems bring me to the main question that I'm going to try to address in the remaining of the talk. And that is, can we use a different tool, something that was overlooked for decades, and improve the gap and perhaps reduce the effect of the smooth potential? And here I'm going to claim absolutely no priority in the idea, and I will explain why a bit later. But before that, I will need to introduce a slightly different implementation of Majoranas, which is going to be relevant for the discussion. So this is an idea worked out by Falko Pienka, and there were a lot of other authors. I think Adi Stern was the one of the leaders of the collaboration. So the idea is the following. Instead of having one superconductor and requiring the magnetic field that is larger than the full induced superconducting gap, they considered two superconductors in a Josephson junction and creating Majoranas in the normal area between the two superconductors. The advantage of this system is the following. If I apply a phase difference of exactly pi, the induced superconducting gap in the middle region is fully suppressed. So I have a system which is in a good contact to a superconductor, but at the same time, magnetic field has no competition with a superconducting gap, and you do not need to apply a large magnetic field to first close the gap. You start basically exactly at the point where the topological phase appears. And indeed, in the ideal case, the authors of this paper have concluded that if I apply a phase difference of exactly pi, then already at zero magnetic field, a topological phase should appear. So this is great. And there were two follow-up experiments trying trying to observe this behavior. One from the Copenhagen group led by Charlie Marcus, another one from the group of Amir Yacobi. But neither of the experiments has seen they both saw something potentially interesting, but neither saw a well-developed superconducting gap. Which brings me to a potential reason for why a superconducting gap may be small. And this is something that has been known since '63. And this was observed by Dejean when studying the density of states in a superconducting vortex. A superconducting vortex is very similar to a is like a three-dimensional Josephson junction. There's a phase winding instead of a discrete phase difference. There's a normal region, which is the vortex core. And the property that they share is that trajectories that go almost parallel to the normal region essentially never see a superconductor. So if the density of states in the normal region is sufficiently large, so that the Fermi wavelength is sufficiently small, and we can think of quantum waves in terms of their quasi-classical trajectories, this argument applies very well. So if I would have a perfect classical infinite density and infinite length vortex, a straightforward calculation shows that the density of states near zero energy should vanish linearly. This phenomenon was called a soft gap in the superconducting literature. This was known since 1963, but it applies to the modern Majorana devices all the same. And this is something that we have to worry about. What are the ways to counteract this? Well, first of all, reducing the electron density in the proximatized region would increase the Fermi wavelength, would enhance the 0-point motion in the direction perpendicular to the junction, and would result in a finite gap. Unfortunately, bringing the system to a low density regime makes it much more sensitive to inhomogeneities of the local potential, because, well, if the density is slightly lower here and slightly higher there, you might have, for example, just a trivial insulating phase over here, topological phase there. Everything behaves worse. Another way to counteract this long trajectories is also known for a long time, and that is to add disorder. So if, for example, imagine this very long trajectory, and imagine it encounters a scatterer somewhere over here. A scatterer will reflect this trajectory at a random orientation and will result and will truncate its length. So the problem about disorder is that you need just the right amount. Well, if the disorder is too weak, it does not have an effect. But if the disorder is too strong, it will spoil the topological properties by itself, because disorder with superconductivity, with broken time reversal symmetry, this is does not generically result in a gap system. And now here is a practical problem, approaching an experimentalist and saying, hey, can you please perhaps add disorder to your system, but just the right amount? If you're a theorist like myself, I do recommend to try this once, but don't expect an enthusiastic response. So disorder, while it works, it's still tricky. Here comes the alternative proposal, and that's the brain behind the idea. Tom Lavin, who was at this point at that point doing a master's project in my group, and he said, "Well, if these long trajectories are so bad, can we perhaps change the geometry, make it into a zigzag?" And in a zigzag, observe, Anton, long trajectories do not appear. So that was the idea. And I'm not proud about myself. I said, totally not gonna work. Just gonna break everything. What kind of crazy device is that? No Majoranas here. I mean, these segments, look at them. They're misaligned. Magnetic field goes wildly. Just gonna break everything. Well, but I'm not too ashamed of myself, because I also appended this with a statement, but you know what? Go ahead and try. See for yourself. Fast forward, I think, a few weeks after, and Tom comes back. And he tells, here is what is happening. So now we are going to look at the band structures. So let me guide at what you see now. So this is the dispersion relation zoomed in close to zero energy. So we have two families of curves. The blue one corresponds to a conventional junction, no phase difference, no magnetic field, trivial regime. The orange one is some magnetic field applied to create a topological phase, and a phase difference of pi to be right in the spot where the topological phase is developed the best. So now here you see that the gap is relatively large, close to k equals to 0. But when momentum is comparable to the Fermi momentum in the device, there is indeed a tiny gap, which is a good 2 orders of magnitude below the parent superconducting gap, even without magnetic field. Now, to compare this band structure to a zigzag device, I need to observe that the zigzag has a much larger unit cell. So this is a single period of a zigzag. So if I want to plot these on the same axis, I need to fold this unit cell, which gives me a basically wrapping these levels around many times, which gives me a soup of levels, but you still see the 2 lowest energy ones. And you actually see that here we didn't even have enough resolution to see the correct topological gap. The topological gap is even much smaller. That is still in a straight junction. Now let's turn on the zigzag shape modulation. So this is what happens if we make the shape, if we shift different parts of this junction up and down by half its width. So we are not yet at a fully developed zigzag, but somewhat close. The difference at these low energies is quite dramatic. Now, of course, I'm now coupling a whole lot of these states, but quite impressively, the superconducting gap is now perhaps it's a bit hard to see here, but perhaps an order of magnitude larger. Now, if we enhance, if we increase the modulation even more, we see almost nearly flat band. These are likely states that are localized to each individual segment of the zigzag. And a superconducting gap that is easily an order of magnitude larger than the other one. So this is quite nice, and impressively, it also works at high magnetic fields. Okay, I say, Tom, that's fine, but does it really have Majoranas? Well, let's see. So the easiest way to check if there are Majoranas is to look at the wave function in such a device. So let me guide you through these plots. So here, the gray areas are the superconductors. The wave function decays strongly inside the superconductors. The white areas in the middle are the normal regions, and unfortunately I see the contrast in the slides is not extremely high, so it's perhaps a bit hard to see. But here you see we are looking at a zigzag device. Here there's also a shape modulation, but it's more sinusoidal. And here this is perhaps the hardest to see. The edges of the superconductors are rigged, so the boundary is disordered now. And yet, in all of these geometries, there are indeed states localized at the edge, with their energy being exponentially small. So if we extract the spatial extent of these edge states, then in a straight junction, they are localized at a length of tens of microns, which is larger than most of my experimental colleagues like to make their devices or make their Josephson junctions. Whereas with zigzag modulations, the spatial localization length of these states is roughly comparable to a single segment of the zigzag pattern. Likewise, the topological gap is once again a good order of magnitude larger. All right, I say, that's great. This is wonderful. Majoranas are there. But maybe you just were very lucky with the parameter choices, and somehow you chose this one value where the Majoranas appear, and otherwise everything looks bad. So now we are looking, let's look at the topological phase diagram of a straight device and compare it to the zigzag device. So what we are plotting, what you're viewing over here is the magnitude of the gap in different regimes. And perhaps, so the color scale here is shared. So you perhaps can immediately see that the gap in the straight junction is an order of magnitude lower overall. But you also see a pattern of phase transitions. These are these lines. So these two panels show how chemical potential in the middle region and the magnetic field control appearance and disappearance of Majoranas. So this is the famous large topological region that appears at the phase difference of pi. So it appears already at a very low value of magnetic field. So this specific point is the one that is most beneficial for the appearance of Majoranas in a Josephson junction. That is actually the maximal gap. And the wave function corresponding to this point is plotted over here. This is the same phase diagram in a Majorana device. And first of all, you see that the topological phase transition have overall a very similar shape. In other words, and this is what actually surprised me quite a lot, we distorted the system geometry rather wildly. We started with a straight junction and we changed it quite a bit. And yet somehow for the Majorana properties, it did not seem to matter at all. The only visible change is that everything became much better. Now, similarly, we could vary the superconducting phase and fix a chemical potential. And also in this case, we observed that the topological phase diagrams look very similar. The differences here are somewhat more visible, but also in this parameter range, the Majorana properties are a good order of magnitude better. So this brings me to my conclusion. I hope I have explained that, well, first of all, I started with observing that there are several problems with Majoranas in straight junctions, with the simplified story of Majoranas. The gap is small, it's sometimes hard to measure. There are quasi-Majoranas that are obscuring the signature. And I hope I have explained how changing something, changing the geometry that was overlooked for 6 decades almost, changing the geometry of the device enhances the gap by an order of magnitude and makes everything much better. Thank you very much. This is it. Are there any questions?
Thank you, Anton, for the very nice colloquium. It was really, really interesting to see this really neat trick to increase the topological gap. So now we have time for questions, and you can use the raise hand button in the participants button to ask questions.
Okay, can I have one quick question?
Please.
Yep, sure.
All right. Well, it's very interesting, but it's more intriguing actually to make such a structure, the zigzag structure. Do you require to have it atomically sharp or atomically clean? So the main point is that you keep the zigzag geometry, or and you don't worry too much about, let's say, a certain level of local disorder, or I mean, so is it tolerant to some degree of local disorder, or this is a requirement or a prerequisite to have Majorana still?
We have so we do know that, first of all, enough disorder will kill Majoranas no matter what. In particular, if the mean free path is shorter than the distance between the superconductors, then nothing is expected to work. But otherwise, we did investigate the effect of the disorder, and we observed that weak disorder, let's say disorder that is in the regime that would enhance Majorana properties in straight junctions, so disorder up to a certain minimal threshold, seems to not do a lot in the zigzag device. The fabrication and precision, once again, unfortunately, the contrast is low, but the boundary of the superconductor here is already quite disordered. It's rigged. And also that did not seem to matter. So the reason for this is, so what does matter quite a lot is the quality of the interface between the region that is in contact with the superconductor and the uncovered region. So to summarize, the geometric details do not matter. Disorder is a potential danger for, well, not danger, is a potential complication here, but it's to the best of our understanding, not anyhow worse than in the usual devices. Now, as far as the fabrication goes, turns out that so once again, this may seem like a crazy theorist idea to start with such a junction and make it into a zigzag. But most of these devices are fabricated by using pattern generators, where the complexity of the
I think it's possible to generate such a pattern by using epitaxy. The angle is what? Is 120, right?
The angle of the zigzag segment.
The zigzag pattern,
here it's about that much. One can make the angle a bit higher. So admittedly we did not do an extremely systematic job investigating what exact geometry is optimal. And this is something that we really should do and will do as a follow-up work.
Okay, thank you.
But indeed, actually quite, I think, at least 3-4 groups were motivated enough to say, hey, I could fabricate a zigzag, let me just try it. Haven't heard about results so far, yeah, hopefully.
It needs it needs just the right combination of material and the substrate. So
yeah, the material is so this does not solve magic. This is not a magical recipe for solving all problems. Most of the problems still remain.
thank you. Thank you.
Hi, Anton. So I have a question. So you were studying basically a zigzag, right, kind of hole, right? But I mean, what happens if you put, let's say, completely disordered interface? So I mean, not completely disordered, but something that changes the width in a smooth way, but in a somehow random way.
So the specific width of the junction here also does not seem to play an important role. There was actually a work that perhaps, let me see if I can draw. There was a relatively recent work from the group of Tudor Stanescu that was doing something like this. So they did a periodically modulated shape. And also in this shape, they have observed enhancement of the gap, but I don't think it was quite as large as in the zigzag geometry, because I think because this geometry doesn't actually prevent trajectories traveling at the grazing angles to appear. As far as the zigzag geometry goes, once again, as far as I understand, the geometric details don't matter. It's actually interesting. So one could reformulate your question in the following way. Let's say I want to put Majoranas into a certain area. So I have this much length to separate them spatially. What is the optimal trajectory of the Josephson junction? So how should I form it so that the Majoranas are as localized as possible near the edges? Now, this is a rather hard problem because we are working in the quasi-classical regimes where Majoranas are an interference pattern of standing waves, and trapping these is rather hard. So still, this is something, this interference pattern means that if I do something, so I cannot use some kind of local optimization, just optimize the local topological gap and be happy with it. Still, this is something that I'm very much interested in trying.
Yes. All right. So thanks a lot. So we have time for some other questions.
Well, I had one question. So could you somehow imagine how to move the Majoranas in a geometry like this?
So that is the topic I did not cover at all, namely the use of Majoranas for topological quantum computation. And the answer is, please don't move Majoranas. Turns out that there are several. So perhaps for those of you who are not very familiar with Majoranas, let me also explain some background about this question. In addition to their protected properties, Majoranas also are non-abelian particles, which means if I take two Majoranas and interchange them, the many-body quantum state of the complete system changes in a discrete fashion. So this principle is used as a basis for implementing some of the quantum gates in a hypothetical Majorana quantum computer. Now, there are several interesting things to know about Majorana-based quantum computers. The most overlooked, the statement that was overlooked, I think, for the longest time, and there was one person, David DiVincenzo, who knew this well, and from whom I repeatedly heard the same statement, who was saying the same thing. Majoranas are on the level of Hamiltonian non-interacting fermions. Non-interacting fermions cannot give a quantum computer. So in order to make a quantum computer with Majoranas, one needs to have to make them to introduce quartic terms. In condensed matter context, there's only one interacting term, and that is charging energy. So in order to make a quantum computer with Majoranas, we would need to use a Coulomb blockade. And there were several works proposing different progressively change with different ideas how to incorporate Coulomb blockade in Majorana manipulation. But the final point on which everything converged was, let's say, a collection of schemes where you never move individual Majoranas, but you rather control couplings between the Majoranas that are close to each other. So imagine you have like one zigzag over here, and you have it terminated with a tunnel barrier, and you lower and raise this tunnel barrier to make this Majorana coupled to another one. This is turns out this together with Coulomb energy is sufficient to create to mimic braiding of Majoranas, so controllably moving them around. And Coulomb energy is also necessary to create a quantum computer. So, so moving Majoranas is in fact not a building block of a quantum computer. Isolating them is.
Right. Thanks. So there's another question by Bruno. Bruno, please go ahead.
Hi. Thank you for the talk. So one question. Would it be possible to generate this same phenomena, but instead of manipulating the geometry of the wire, by applying some sort of modulating potential?
Well, let's see how we do that. Let me think. So let's go to the geometry. So this is the geometry. What we want to, I think the starting point of working with quasi-classical trajectories is reasonable. So we want to somehow make the geometry such that we eliminate the straight trajectories. The naive thing to do this would be by applying a magnetic field so that they bend, an out-of-plane magnetic field. But in superconductors, a magnetic field is rather bad. It makes the trajectory of an Andreev reflected particle different, and probably will cause a lot of problems. So this is probably not a good idea. Now, of course, another opportunity is to apply an electrostatic potential. And there I can imagine something working. Say if I apply an electric field that bends the electrons upwards here, an electric field that bends electrons downwards here, and perhaps the strength of this electric field is such that the amount of displacement or amount that every trajectory is bent by a sufficiently large angle. So now this could potentially result in the exact same physics. So that means the answer to your question is yes. I haven't actually thought about it. Now, how it will work in practice, I'm not entirely sure. So likely yes, but one needs to try.
Okay, thank you.
There's another question by Shavuk. Shavuk, please go ahead.
Hey, I have one question related to this zigzag geometry you showed. So I was wondering if the sinusoidal geometry, for example, what happens if now this geometry looks like they are like same phase. If you change the phase of that sinusoidal geometry, what will happen? It improves more, or? Sorry,
what do you mean by the same? Are you talking about the phase of the sine, or
yeah, exactly.
Oh, so I think this is roughly this geometry that was considered by Tudor Stanescu and his collaborators, and it seems like it also has some enhancement of superconducting gap, but I think it is smaller than in a zigzag. The reason for this, once again, is the motivation for the zigzag shape. Namely, our goal is once again to eliminate straight trajectories. If I make the different edges modulate in phase, I do not eliminate trajectories that fly through the device. So I tried to illustrate this in here. So in such a shape, I can still have a particle that flies directly through without ever encountering superconductors. Such particles are only coupled to superconductors via 0-point motion and therefore have a rather small gap.
Okay, thank you.
Now it turns out that I have to say this is my intuition about it. Again and again, my intuition about these devices, as well as the intuition of other people, was wrong, and it turns out these geometries do enhance the superconducting gap, but not as much as a zigzag.
Okay, thanks.
There's another question by Chakrandar. Chakrandar, please go ahead.
Thank you for a wonderful talk, Professor. So I had a question regarding the quasi-Majoranas. So you referred that they are very similar to Majoranas, but are spatially not separated. So can
Correct.
you shed more light about the properties?
Let's see. So, well, there has been a debate in the community about these states. First of all, depending on the different parameter regimes, they could still be separated. For example, you can view in one limit, you can view quasi-Majoranas as isolated Majoranas appearing in different spin split bands. And one can find a regime where the potential is sufficiently smooth, where the two quasi-Majoranas one belongs to, say, spin down band, another one belongs to a spin up band, and they're spatially separated by roughly Zeeman energy divided by the electric field at the edge of the system. Turns out, however, that quasi-Majoranas are more universal than just than that. And they appear also in a regime where the Zeeman splitting is smaller or the electric field is larger. And they can sit almost exactly on top of each other, but still belong to orthogonal spin bands. And have an almost zero overlap or an exponentially small overlap due to having different Fourier components due to being made out of different Fourier components of the wave function. So these are separated in the K space, and since the potential is smooth, different K vectors only couple adiabatically, or only couple weakly, and therefore allowing to incorporate two almost degenerate or almost isolated states at nearly the same position.
Do they have the same structure of creation annihilation operator as Majoranas?
Yeah, right. So each of every of these. So quasi-Majoranas is perhaps not the best term. A more precise one would be a pair of non-topological coexisting Majoranas, something like this. So these are honest to goodness Majoranas. In fact, if one somehow managed to completely isolate one of these two and ensure that these two never couple and this one also never couples to the outside, one would be able to make exactly the same topological quantum computer. The problem here is, of course, that it's much harder to guarantee this, because now all of a sudden you do need atomic scale control over system. You do need it to be pristine. You have to worry about the local noise and the coupling. So So it's a much harder way to go.
Okay,
But
thank
still,
you.
each of these two is a perfect Majorana operator.
Do they annihilate each other if they come close in space? Doesn't they annihilate each other?
Yeah, well, Majoranas don't annihilate each other. They couple and split. So if I start with two isolated Majoranas, I look at the spectrum of a system as I move them closer together, they split into a single fermionic level, which depending on the many-body state could be occupied or empty.
Sure, okay,
So,
thank you.
yeah.
Yeah.
All right, so I think that we can now close the official part of the colloquium. So we are going to stop the recording, but we are going to keep this session open. So in case you want to ask any other questions.
By all means, I am still around. So if you want to ask anything.
Yeah. So before stopping the recording, let's thank Anton for the very nice colloquium on this very neat way of creating robust Majoranas. And let me remind you that the colloquium next week will be at 5 in the afternoon CEST time, and will be given by Evan Gray. And with this, thank you everyone for coming, and see you next week.